This study resource on acids-bases focuses mainly on the fundamentals of acids, bases, and salts. It covers the subtopics in this area and includes several solved problems in the material, as well as exercises for learners to try, with answers provided. The contents in this study include introduction, major acid-base theories, strength of acids and bases, Amphoterism, classification of acids based on chemical sources of constituent elements, binary acids, Hydracids, Oxyacids, Oxoacids, pH and pOH scales, polyprotic acids, bases, and solutions of salts, polyprotic bases, the strength of acids and bases, buffer solutions, buffer capacity, Henderson-Hasselbalch equation, acid-base titrations, acid-base indicators, exercises. Introduction. Let us start with the differences between acids and bases. Acids have a sour taste, while bases have a bitter taste. Acids turn blue litmus red, while bases turn red litmus blue. The pH of acids is less than 7, while the pH of bases is greater than 7. Acids react with active metals to release hydrogen gas. Bases feel slippery in solution. Acids react with bases to form salt and water, and bases also react with acids to form salt and water. Solve problem 1. Where do we meet acids and bases? Solution to solved problem 1. We meet acids and bases in the following: lemon juice and vinegar, acidic substances in food; soap and detergent, common household substances; antacid tablets, used to reduce excess stomach acid; blood and saliva, examples of body fluids whose pH must be controlled; laboratory titration, a method used to find an unknown acid or base concentration. Solve problem 2. Is every sour substance an acid? Solution to solve problem 2. Many sour substances are acidic, like lemon and vinegar, but acidity should be confirmed using litmus paper, pH paper, or a pH meter. The figure here is a practical example of how a litmus paper, pH strip, and pH meter are used to measure the pH of a solution. The solution measured here is acidic, with a pH of 5.5. Solve problem 3. What gas is released when zinc and sodium metals react with hydrochloric acid differently? Solution to solve problem 3. For the reaction with sodium metal, hydrogen gas is released, while for the reaction with silver metal, no gas is released and there is no reaction because silver is below hydrogen in the electrochemical series, so it cannot displace hydrogen from an acid. 2.0. Major acid-base theories. The 3 main acid-base theories below will be considered in this study: Arrhenius theory, Brønsted Lowry theory, Lewis theory. 2.1. Arrhenius theory. The Arrhenius theory states that an acid is a substance that produces hydrogen ions when dissolved in water. An example is the dissolution of hydrochloric acid in water, as shown here. A base is a substance that produces hydroxide ions when dissolved in water. An example is the dissolution of sodium hydroxide in water, as shown here. 2.2. Brønsted-Lowry theory. The Brønsted-Lowry theory states that an acid is a substance that donates a proton, hydrogen ion, and a base is a substance that accepts a proton, hydrogen ion. Example: consider the deionization of hydrochloric acid in water, as shown here. Hydrochloric acid donates the proton and becomes a chloride ion, while the water molecule accepts the proton and becomes a hydroxonium ion. Also, a water molecule can act as an acid, as in the dissolution of ammonia, where it donates a proton and the ammonia accepts it, as shown here. Simple memory tip from Brønsted-Lowry theory: acid gives a hydrogen ion. Base receives a hydrogen ion. In the first and second equations, hydrochloric acid and water, respectively, donate hydrogen ions, so both are acids. Also, in the first and second equations, water and ammonia, respectively, accept hydrogen ion, so both are bases. 2.2.1 Conjugate system. The resulting species of bases and acids during acids and bases dissociation, respectively, are known as conjugate bases and conjugate acids, as seen in equations 1 and 2 here. This is the conjugate seesaw phenomenon. The conjugate seesaw means that when an acid donates H, its resulting species on the product side of the equation becomes its conjugate base, while the resulting species on the product side of the equation for the base that accepts H becomes its conjugate acid, as shown here. 2.3 Lewis theory. The Lewis acid-base theory states that a Lewis acid is a substance that accepts a pair of electrons. A Lewis base is a substance that donates a pair of electrons. Simple memory tip. Lewis acid accepts electrons. Lewis base gives electrons. In the reaction shown in equation 3 here, barium fluoride is the Lewis acid because it accepts an electron pair. Ammonia is a Lewis base because it donates a lone pair of electrons from nitrogen. The bond formed is called a coordinate covalent bond or dative bond because both electrons in the bond come from the same atom. Note the following. Arrhenius theory is useful when the reaction is in water. The Brønsted-Lowry theory is broader because it focuses on proton transfer. Lewis's theory is the widest because it focuses on electron pair transfer. Easy equation memory, Arrhenius memory, acid gives H+, base gives OH in water. Brønsted-Lowry memory, acid gives, base receives. Lewis memory, Lewis acid accepts electrons, Lewis base gives electrons. Solve problem 4. In Brønsted-Lowry theory, what does a base do? Solution of solve problem 4. It accepts a proton, example a hydrogen ion, 3.0. Strength of acids and bases. Acids and bases are classified according to their strengths, with the use of the words strong and weak. So we have strong acids and strong bases, as well as weak acids and weak bases. In chemistry, the strength of an acid or base depends on how much it ionizes in water. A strong acid or strong base ionizes almost completely in water. A weak acid or weak base ionizes only partially in water. 3.1. Strength of acids. A strong acid completely releases hydrogen ions in water. A weak acid only partially releases hydrogen ions in water. Examples of strong acids: hydrochloric acid, nitric acid, sulfuric acid. Examples of weak acids: organic acids, example, ethanoic acid, carbonic acid, hydrofluoric acid. Illustration of equations 4 and 5 to describe the strength of acids, using hydrochloric acid as a strong acid and ethanoic acid as a weak acid, as shown here. The complete dissociation of strong acids is often shown with irreversible arrows in the hydrolysis reaction equation, while the incomplete dissociation is often shown with reversible arrows. Explanation. HCl is a strong acid because almost all HCl molecules donate their proton to water, and ethanoic acid is weak because only some of its molecules ionize in water. The reversible arrow shows partial ionization. 3.2. Strength of bases. A strong base completely produces hydroxide ions in water, while a weak base only partially accepts protons or partially produces hydroxide ions in water. Examples of strong bases: sodium hydroxide, potassium hydroxide, calcium hydroxide. Examples of weak bases: ammonia, methylamine. Illustration of equations 6 and 7 to describe the strength of bases, using sodium hydroxide / calcium hydroxide as strong bases and ammonia as a weak base, as shown here. Explanation. NaOH is a strong base because it dissociates completely in water to produce OH ions. Ammonia is a weak base because only some ammonia molecules accept hydrogen ion from water to form ammonium ion and hydroxide ion. Note the practical comparison below. HCl in the laboratory is much stronger than vinegar at the same concentration. NaOH is a strong base, while ammonia solution is a weak base. 3.3. Amphoterism. Amphoterism is the ability of a substance to behave both as an acid and as a base, depending on the substance it reacts with. A substance that can act this way is called an amphoteric substance. Simple memory tip: amphoteric psygroi can act both ways. It can donate H like an acid or accept H like a base. Examples of amphoteric substances are water, aluminium hydroxide, and zinc oxide, illustrating the effects of water, aluminium hydroxide, and zinc oxide as amphoteric oxides. Example: water as an amphoteric substance. For water, recall the reactions in equations 1 and 2. In equation 1, it behaves like an acid, and in equation 2, it behaves like a base. Aluminium hydroxide as an amphoteric hydroxide. Amphoteric properties of aluminium hydroxide with hydrochloric acid and sodium hydroxide are shown here. 4.0. Classification of acids based on chemical sources of constituent elements. Generally, acids can be sourced from organic matter known as organic acids. Example, the alkanoic acids containing the carboxyl group, ethanoic/acetic acid found in vinegar, methanoic/formic acid, benzoic acid, citric acid, and alcohols are known to be weakly acidic but not classified as organic acids, or from inorganic or mineral substances known as inorganic acids. Example, hydrochloric acid, hydrogen trioxocarbonate acid. More so, acids can be classified based on the chemical nature/source of their constituent elements as follows. 4.1. Binary acids/hydracids. These acids contain hydrogen and only one nonmetal element. They do not contain oxygen. Examples of binary acids/hydracids: hydrochloric acid, hydrobromic acid, hydroiodic acid, hydrosulfuric acid. 4.2. Oxyacids/oxoacids. These acids contain hydrogen, oxygen, and another central element, usually a nonmetal. Examples of oxyacids/oxoacids: sulfuric acid, nitric acid, carbonic acid, phosphoric acid, perchloric acid. Solve problem 5. Why is vinegar called a weak acid? Solution to solve problem 5: because ethanoic acid ionizes only partially in water. 5.0. pH and pOH scales. The pH of an acid is equal to the negative logarithm to base 10 of its hydrogen ion concentration. Equation 6. Similarly, the pOH of a base or an alkali is equal to the negative logarithm to base 10 of its hydroxyl ion concentration. Equation 7. Equation 8 shows that at room temperature, 25 degrees Celsius, the sum of the pH and pOH of a substance equals 14. The table here should make you feel good about the way some of these substances taste. Lemon juice is sour, vinegar is sour, pure water is tasteless, baking soda solution is bitter, and soap solution is bitter. Note the following memory tips. Low pH means high acidity. High pH means high base. pH 2 is strongly acidic. pH 12 is strongly basic. Solve problem 6. What is the pH of a neutral solution at 25 degrees Celsius? Solution to solve problem 6. The pH of a neutral solution at the considered temperature is 7. Solve problem 7. The hydroxide ion concentration in a solution is 0.0001 molar. What is the pOH of the solution? Is the solution acidic, basic, or neutral? What is the pH of the solution? Solution to solve problem 7, we use equation 7. Step 1, plug in the value of the concentration of hydroxyl ion equals 0.0001 molar. Step 2, use the logarithm rules and evaluate for pOH accordingly. Step 3, interpret it. At 25 degrees Celsius, pOH 7 out basic, pOH for 7 neutral, pOH 7 acidic. Since pOH for 4 times 0, which is less than 7, the solution is basic. You can find pH using EQ 8. This gives pH as 10. This confirms that the solution is basic. 6.0. Polyprotic acids, bases, and solutions of salts. 6.1. Polyprotic acids. Polyprotic acids are acids that can release more than one proton hydrogen ion. Examples: sulfuric acid, phosphorus acid, hydrosulfuric acid, carbonic acid, etc. Example: consider the dissociation of sulfuric acid at 25 degrees Celsius, as shown here. It is observed that sulfuric acid in step 1 is a strong acid by the amount of its acid dissociation constant shown here, while hydrogen tetraoxosulfate Vi ion in step 2 is a weaker acid. This shows that the sulfate component reduces the ease of the acid to give out protons. This proves that sulfuric acid releases the first proton much more readily than the second, as Ka1, Ka2. 6.2. Polyprotic bases. Polyprotic bases are bases that can accept more than one proton, hydrogen ion, or produce more than one hydroxide ion during acid-base reactions. For example, calcium hydroxide is polyprotic because it has 2 hydroxide groups and can neutralize 2 protons or hydrogen ions. Other examples of polyprotic bases are as shown here. 6.3. The strength of acids and bases. The acid dissociation constant, Ka, in equation 10, obtained from the equation 9, shows the dissociation of a weak acid, which measures how easily an acid releases hydrogen ions in water. Similarly, equations 11 and 12 show the dissociation of a weak base and its base dissociation constant, Kb, respectively. For a weak acid dissociates only partially in water, while a strong acid dissociates almost completely in water and produces many hydrogen ions. The Ka value of a strong acid is greater than that of a weak acid. So, the higher the Ka value in equation 10, the stronger the acid. The base dissociation constant, Kb, in equation 12, measures how easily a base produces hydroxide ions, or accepts hydrogen ions in water. The Kb value of a strong base is greater than that of a weak base. So the higher the Kb value, the stronger the base. The table here shows increasing strength of acid and bases with increasing values of the Ka and Kb values, respectively, at 25 degrees Celsius. Meaning of increasing acid strength. The arrangement moves from the acid that releases hydrogen ion least easily to the acid that releases hydrogen ion most easily. In terms of constants, acid strength increases as Ka increases, or as pKa decreases. Important note, for very strong acids in water, The solvent has a leveling effect, so all may appear to ionize completely. The relative orders below are based on general acid strength trends and approximate first dissociation pKa values where useful. Solved problem 8. The table here shows the verified order of increasing acid strength for some acidic substances. Provide a fourth column to give reasons for each arrangement. Solution to solved problem 8. The reasons the displayed order are as follows. 1. Hydrogen chloride, hydrogen bromide, and hydrogen iodide become stronger down group 17 because the hydrogen halide bond becomes weaker and the conjugate base becomes larger and more stable. Hydrogen sulfate is also a strong acid in its first dissociation, but its first pKa is less negative than those of hydrogen chloride, hydrogen bromide, and hydrogen iodide. 2. For hydrohalic acids, acidity increases down the group. Although fluorine is very electronegative, the hydrogen fluoride bond is very strong, so HF is much weaker than HCl, HBr, and HI. 3. For group 16 hydrides, acid strength increases down the group because the hydrogen electronegativity bond becomes weaker and the conjugate base becomes larger and more polarizable. 4. Oxoacids become stronger when the central atom has more electron-withdrawing oxygen atoms and when the conjugate base is more resonance stabilized. Perchloric acid is the strongest in this set. 5. These are hypohalous acids with the same hydrogen-oxygen bond, oxygen-halogen bond pattern. Acid strength increases as the halogen becomes more electronegative. Cl greater than Br greater than I. 6. For chlorine oxoacids, acidity increases as the number of oxygen atoms and the oxidation state of chlorine increase. More oxygen atoms withdraw electron density and stabilize the conjugate base by resonance. 7. Sulfuric acid is stronger because sulfur is in the +6 oxidation state and has more oxygen atoms than sulfurous acid. The sulfate conjugate base is better stabilized. 8. This order refers to the first acidic proton. The phosphorus-hydrogen bonds in hypophosphorus acid, H3PO2, and phosphorus acid, H3PO3, are not normally acidic. Only OH hydrogens ionize. Approximate first pKa values place H3PO2 and H3PO3 as stronger first proton donors than phosphoric acid, H3PO4. 9. Ethanol is only very weakly acidic because its conjugate base, ethoxide, has no resonance stabilization. Ethanoic acid is much stronger because the ethanoate ion is resonance stabilized. 10. Chlorine atoms withdraw electrons by the negative inductive effect and stabilize the carboxylate conjugate base. More chlorine atoms mean stronger acid. 6.5. Solutions of salts of acids and bases. 6.5.1. Polyprotic acid salts solutions. It is shown here that salts made of strong acids and strong bases have the nature of a neutral solution, maintaining the red and blue colors of litmus paper. Quantitatively, the acid dissociation constant of the acid that makes the salt is equal to the base dissociation constant of the base that makes up the salt, Ka, Kb. The cases for solutions of other salts from their combined acids and bases are as shown in this table. Practical case: NaCl solution is approximately neutral. Ammonium chloride solution tends acidic and is used in some dry cells. Aluminium salts used in water treatment can make water acidic because small, highly charged cations hydrolyze water. Solved problem 9. Is sodium chloride solution acidic, basic, or neutral? Solution to solve problem 9. It is approximately neutral because it comes from a strong acid and a strong base. 7.0. Buffer solutions. A buffer is a solution that resists sudden changes in pH when small amounts of acid or base are added. We have acid buffer solutions. These are made from solutions of weak acids and a soluble salt of its conjugate base. These are obtained when the buffer action occurs at pH 7. An example of an acid buffer is the mixture of ethanoic acid and sodium ethanoate. We also have base buffer solutions. These are made from solutions of weak bases and a soluble salt of its conjugate acid. For base buffers, their buffer actions occur at pH 7. Example of a base buffer is the mixture of ammonia and ammonium chloride solution. The two equations here show the preparation of a buffer solution for action to maintain the pH of solutions. Considering the ethanoic acid/sodium ethanoate buffer solution, we will have that the ammonium salt will dissociate completely in solution to produce a high concentration of ethanoate ions, while the high concentration of ethanoic acid incompletely dissociates in solution to give a low concentration of the ethanoate ions. Note that a base buffer solution will show the same preparation as will be shown practically for an ammonia/ammonium chloride buffer solution. Example of an acidic buffer pair is ethanoic acid/sodium ethanoate. Example of a basic buffer pair is ammonia/ammonium chloride. The illustration here shows how prepared ammonia/ammonium chloride buffer solution resists changes in pH when small amounts of acid or base are added. It first shows the buffer mixture containing ammonia and ammonium ion from ammonium chloride. The buffer is shown as a basic buffer with pH close to 9.25. When acid, hydrogen ions, is added, the ammonia component reacts with it to give ammonium ion. This removes the added acid and prevents a sharp fall in pH. When base, hydroxide ion, is added, the ammonium ion reacts with it. This gives ammonia and water. This removes the added base and prevents a sharp rise in pH. So ammonia protects the solution against added acid, while ammonium ion protects the solution against added base. This is why the ammonia/ammonium chloride buffer maintains a fairly stable pH. The practical illustration of buffer solutions in real life is as follows. Human blood resists sudden pH change because it contains buffer systems. Saliva contains buffer systems that protect the mouth from sudden acidity. Shampoos and pharmaceutical syrups are formulated with pH control in mind. Swimming pool water is adjusted to avoid harmful acidity or basicity. 7.1. Buffer capacity. This is how much acid or base a buffer can absorb before its pH changes greatly. Example. The buffer capacity of ammonium chloride solution depends on the amount of ammonia and ammonium chloride present. A more concentrated buffer has a higher buffer capacity, while a dilute buffer has a lower buffer capacity. Solve problem 10. What two components usually make an acidic buffer? Solution to solve problem 10. A weak acid and its salt, such as benzoic acid, sodium benzoate, formic acid/sodium formate, etc. 7.2. Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is used to calculate the pH or pOH of a buffer solution. It shows how the pH of a buffer depends on the ratio of the weak acid/base and its salt or conjugate partner. The equations here show the Henderson-Hasselbalch equation for calculating the pH and pOH of buffer solutions respectively, where HA, weak acid, A to negative power, conjugate base or salt, pKa, log Ka, B, weak base, BH to positive power, conjugate acid or salt, pKb, log Kb. Solve problem 10. Calculate the pOH of a buffer solution containing 0.20 molar ammonia and 0.10 molar ammonium chloride. Given, Kb for ammonia solution equals 0.00018. Solution to solve problem 10. Step 1. Identify the buffer components. Step 2. Write the Henderson-Hasselbalch equation for pOH for a basic buffer. Step 3. Calculate pKb. Step 4. Substitute the values. So, the pOH of the buffer solution is 4.44, 8.0. Acid-base titrations. Titration is a laboratory method used to determine the unknown concentration of an acid or a base. To be more precise, titration is a volumetric analytical method in which a solution of known concentration is carefully added to a solution of unknown concentration until the reaction is complete. The solution of known concentration is called the titrant. The solution of unknown concentration is called the analyte. The point where the reaction is complete is called the end point or equivalence point. Example, reaction of aqueous hydrochloric acid with aqueous sodium hydroxide to form aqueous sodium chloride and liquid water. From the practical illustration here, the equation below could be used to calculate the amount of the analyte hydrochloric acid, where C is equal to concentration in moles per decimeter cube, V is volume in decimeter cube, and N is the number of moles of the acid and base obtained from the balanced titration equation of reaction. For this practical illustration, 1 mole of hydrochloric acid reacted with 1 mole of sodium hydroxide. This makes the value of N equal to 1 for each. 8.1. Endpoint of the reaction. The endpoint of the reaction is the point at which an equivalent or stoichiometric amount of the analyte is required to react with the titrant to form the salt solution. Oftentimes, the analyte and titrant are colorless, so indicators are required to indicate the endpoints, as solutions of acids, bases, and salts have unique colors in different indicators. The nicely displayed table here shows some available indicators used in acid-base titration, their pK values, colors in acidic, basic, and neutral medium, or equivalent point or endpoint. Learners and viewers should pay attention to these nicely presented colors and appreciate the beauty of chemistry. 8.2. Titration curves. A titration curve is a graph that shows how the pH of an analyte changes as a titrant is gradually added during a titration. In an acid-base titration, the graph is obtained by plotting y-axis, pH of the solution, x-axis, volume of titrant added in milliliters. As the titrant is added drop by drop, the pH changes continuously until the reaction is complete. The shape of the graph depends on whether the acid and base are strong or weak. It is obtained experimentally and reproducible in practice that the titration of a strong acid and a strong base gives an equivalence point pH of about 7. The titration of a strong acid and a weak base gives an equivalence point at pH less than 7. The titration of a weak acid and a strong base gives a variable equivalence point, pH of greater than 7, C, and the titration of polyprotic acid gives more than one equivalence point, D. While the titration of a weak acid and a weak base gives variable equivalent points, with the main factor being the values of the acid dissociation constant Ka and base dissociation constant Kb oozed in the neutralization reaction as shown here. If Ka horn Kb, the equivalence point is approximately pH 7. If Ka Kb, the equivalence point is acidic, pH 7. If Kb Ka, the equivalence point is basic, pH 7. Note the following memory tips. Memory, SASB, strong acid plus strong base gives pH 7. Memory, WASB, a weak acid plus strong base gives pH above 7. Memory, SAWB, strong acid plus weak base gives pH below 7. Solve problem 11. Why do we add an indicator during titration? Solution to solve problem 11. To show the endpoint by a visible color change. Solve problem 12. What is the color of phenolphthalein in an acidic solution? Solution to solve problem 12, colorless. Exercises. 1. The hydrogen ion concentration in a solution is 0.01 molar. Calculate A, the pOH of the solution. B, state whether the solution is acidic, basic, or neutral. C, determine the pH of the solution. 2, calculate the pH of a buffer solution containing 0.20 molar propanoic acid, 0.10 molar sodium propanoate. Given Ca for propanoic acid 0.000013,